Okay, so let's talk about this new topic, which is policy search methods for solving reinforcement learning problems. So the basic idea here is that so far we discussed a lot of methods for computing the value function. So the focus has been on the value function and computing the value function. And we know that if we have, say, the optimal value function, then computation of the greedy computation of the optimal policy would be easy because we can take the greedy policy with respect to that optimal value function, and the solution would, the policy would be essentially optimal policy. So far we only had explicit representation of the value function, and policy was just computed kind of on the fly whenever we needed it. So this is kind of, that was a good idea because we know value functions have a lot of nice properties, like the recursive properties through the Bellman equation, which allowed us to compute them in kind of efficient ways. But there are other methods that are based on explicit representation of the policy. So they're based on explicit representation of the policy and then optimizing the performance of the agent by searching in the space of policy. So if we could say that, like, as a kind of image, mental image, if this was the space of all value functions, previously we were moving around until we get to this point of, say, Q star, and that would be this kind of the procedure to get to the optimal policy, or at least an approximation of it. If we had, say, if we have a function approximation, or if we have samples, we only get to the neighborhood of it. But here the idea is that, so let's start talking about the policy space and represent each policy in some explicit form. And I'm going to show you some examples. So each of these would be one policy, maybe parameterized by some theta, parameter theta. And then the goal is to kind of guide this movement of policies in order to get to the pi star, or an approximation. So policy search methods are basically, we have explicit form representation of the policy, and also the search process would be formulated as an kind of optimization or search in the policy space directly. And we call these methods policy search methods, or like sometimes they may call direct policy search methods or things like that. And of course, there would be methods that would be a hybrid of policy search methods and value-based methods, which are basically, we have both explicit representation of the policy and value function, and we use both of them in order to kind of solve the RL problem. So this is the idea. And we will see that there are some benefits sometimes doing this. For example, if we want to work with large function problems with large action spaces, doing this thing might be actually easier. Okay, so let's talk about policy parameterization. So we consider stochastic policy pi theta, which is a mapping from state space to the space of probabilities over action space. So recall that this M of A means that it's a space of probability distribution defined of action space. And for each X, we have, of course, different distributions, or possibly different distributions. And this policy is parameterized by pi, which belongs to this capital pi, theta, which is belongs to this space of capital theta. So this would be a parameter space. For example, it can be, this parameter space can be a subset of RP. So we use a p-dimensional vector in order to represent our policy. And then given this capital theta, we can get capital pi of capital theta space. So that would be the space of all policies that we have, which are essentially basically saying that we change thetas and we get different policies. So this is space of policies induced by these space of parameters. And then, of course, this space by definition depends on both how this mapping works and what this capital theta is. So by changing the mapping, we get different policy spaces. By changing the size of the parameter space, we get different space of policies. So let's kind of get to some more concrete examples. So there are different choices of parameterizing a policy. A generic example is based on like this softmax or Boltzmann distribution. So we can define it like this. Suppose we have a function f of theta, which is a mapping from state action to a real value number. So this can be, for example, a deep neural network, a decision tree, or any other function approximation or function that you might parameterize by some theta. And then we can define the density of choosing action A at state X as follows. So here, I'm talking about densities, so which basically kind of mean that A is a continuous state space. So for example, A is, for example, m-dimensional action space. So the way that we define it is just we take f of theta, evaluate it at x and a, and take the exponential of it. So we have exponential of f of theta of x and a. So this basically would be a positive number. And then we normalize it to make sure that it's a probability distribution. So the way the normalization works is basically we divide it by the integral or summation of this exponential of f of theta of x and a prime. And a prime is something that we take summation over or take integral over. So just a kind of special case would be when we are talking about, we use a linear function approximator to represent f of theta. So if we write f of theta of x and a as phi of x and a times theta, so and phi of theta, phi of x and a of phi would be feature vector. So it would be p-dimensional feature vector, and theta is say p-dimensional parameters. We get essentially a very similar thing, except that I'm here replacing f with phi times theta. And of course, based on how we choose phi, we can get very different type of policy parameters. I think it might be kind of interesting to see, or kind of maybe more intuitive if we assume that A is a discrete action space, so that in that case, instead of density, pi of theta denotes the probability of choosing some action. So it's not a density, but a probability mass of choosing action A. And it would be very similar to before. So probability of choosing action A at state X would be exponential of phi of xa times theta. And then instead of integral, we have summation, but over A primes. So this is summation over this thing. So this would be a valid for any choice of phi and theta. This would be a valid probability distribution. Okay, any questions so far? Okay, seems to be.
Is there something special about using this particular way to normalize the output, like using the Boltzmann approach?
Okay, so I guess one question is anything is special about Boltzmann. The other is for Boltzmann using this special type of normalization.
I guess you have to normalize to get a probability, right? But there's, you could do it in other ways, I guess.
That's right, and I guess that would be fine. So this is a kind of generic enough family of kind of models, probabilistic models. But if you choose others, that would be okay too. And I'm actually going to show you something that would be a bit, looks at least different. So this is actually, so this would be essentially defining, we can think of it, well, I guess I would say that this Boltzmann distribution, or this form, this is kind of like, we can call it an exponential family that is defined based on that phi and theta are very generic. Many distributions can be written in that way. But as you kind of pointed out, there is no reason to only work with this. So if you come up with some other valid parameterization of probability, that's totally fine.
Sorry. One thing about the formula, the first formula, the integral part in the denominator of the first one is over the continuous space. And in that case, in realistic settings, we'll use a deterministic policy network rather than a probabilistic one, right?
Well, I guess, okay, so I guess there are two things. One is that, so it is true that computation of this integral might be actually difficult because it's an integral over continuous action space. But for some cases, like normal distribution that I'm going to talk about, normal distribution can also be written in this form. But the integral, the normalizer or partition function can be written in analytical formulation, in our analytical way, so we can compute it easily. But then in some cases, we also use deterministic policies instead of stochastic policy. And deterministic policy is a special case of a probabilistic policy with mass centered at some point. So here I just wrote kind of a, I wrote a probabilistic one because it's more general. But then the question of whether we can actually compute this in practice or not for any choice of phi and theta, or for any choice of f here, maybe not. Maybe we cannot compute it and then we have to approximate it. So, but at this level, I just want to talk about representation and not computation. Okay, so another example is suppose we define phi as a normal, defining a normal distribution where the mean and variance or covariance are parameterized by theta. So here, this is kind of easy. Like essentially, we need to have mean would be any function from, say, state space to the space of actions. So that if, say, action space is dA dimensional, so it would be R of dA. So R of, I guess, previous R of 10, for example, if it's a 10-dimensional action space. And then the covariance would be essentially similar mapping, but because its covariance has some properties that it should be positive semi-definite, we have to make sure that our representation keep it positive semi-definite. And in many cases, people may just use, say, identity. So maybe they use some parameter in the form of, say, sigma parameterized square times identity. So this is easier to kind of enforce positive semi-definiteness because it is enough to make sure that this term is non-zero or non-negative. But in general, so this would be kind of normal, this would be a form of normal distribution. And also, we can actually show that normal distribution belongs to the same family of distributions with proper choice of phi. So we can write it that way, I guess. But then the benefit of it would be that it is easy, that normalizer can be computed in a kind of analytical form way. So this is just another example. So one benefit here is that if we work with this policy parameterization, working with continuous action space is going to be relatively easy, or at least it is relatively easy to generate samples from continuous action space. So for example, in the case of normal, as long as I can sample from a normal distribution, given a mean and covariance, which is easy, I mean, computers can do it easily, then I can sample from an action that is continuous. And this is a kind of a difference with value-based methods, because value-based methods say they might be a bit difficult to work with continuous action spaces. And kind of the reason to see why is that suppose you know the optimal value function, action value function, so I give it to you, but action space is continuous. So action space is R10, for example. How are you going to compute the optimal policy? We are going to compute the greedy policy, right? So we compute the greedy policy and that would be optimal. But in order to compute the greedy policy, we need to compute argmax of action, which is, for example, is m-dimensional R of whatever Q and A that we have. So here we have to solve a maximization problem in a continuous domain. And if this continuous domain is high dimensional, solving it might be difficult. It is a continuous optimization problem. And one point is that this action value function is not necessarily a nice function. It's not necessarily a concave function that we can easily do gradient ascent to find the global optimal. It might be like this. So solving it would be difficult. Of course, people have done it, so there are approaches to do it, perhaps approximately, but at least a nice framework that we had that assumed that we could compute this argmax is going to be modified a little bit. So also, it is not only for the greedy policy, or computing the optimal policy, but even within value iteration or policy iteration, and all the algorithms that we derive from that, for example, Q-learning, fitted Q-iteration, LSPI, and all those methods, they also require the computation of the greedy policy because of, say, policy improvement step. And then that requires this calculation. So this is kind of make purely value-based methods a bit difficult to work with continuous action spaces. But whereas for, say, explicit policy representation, if we choose some method or some parameterization like a normal distribution, things would become much easier. But I guess, as you mentioned, like if, for example, here, so this is not everything always better. So if we have a generic form for this parameterization of the policy, computation of this integral in general is also as difficult as finding the maximum of action space, of some function over action space. So for any policy parameterization, we are not necessarily in a better situation, but at least for some of those, like, for example, Gaussian or normal distribution, or if we do it like a deterministically, then it would be much easier. Okay, is this clear?
Sorry, a quick question about the Gaussian assumption. Is it in realistic settings, according to your experience, is it like a too strong assumption to make?
Okay, so I guess it's, I don't want to say a very kind of general statement, but it is, it might not be too bad an assumption, because if the problem is an MDP, we know that the optimal value function, sorry, optimal policy is a deterministic policy. And a Gaussian distribution can represent a deterministic policy by just concentrating in very small region. Like when the covariance or variance shrinks to 0, it becomes a deterministic policy. So if we do that, then basically we shrink to the class of deterministic policy, and we know that optimal policy belongs to that space. But there are caveats here. Like if we do this shrinking, then optimization of the policy would become more difficult. So there would be this trade-off. But if we give enough, like if we have a covariance formulation instead of just variance formulation, it works in many domains. I don't want to say in all domains. So if you have a kind of a prior knowledge that this form of policy should work better for your type of problem, you should use it instead of Gaussian.
Yeah, but I see the point here. So when we do shrinking, we only care about the order or the maximum one. We don't care about how exactly the rest of the ones are distributed.
Right, yes, yeah. That's right, yes. But then if we shrink it too much, then optimizing it would become difficult.
I also have a question about this. So the Gaussian distribution has infinite support, but you might want to sample actions in a bounded region of a continuous space. So let's say between 0 and 1, which is a problem I recently encountered actually. What would you recommend in such situations? What I did in that case was I tried two things. I either discretized the range and sampled from a categorical instead, or sample from a Gaussian and then pass through a sigmoid, let's say, and so now you're in a bounded range. But is there a better way to do this?
Well, I guess truncation would not, or not truncation, but discretization would not work if your action space is large.
Yeah, absolutely. In my case, it was 1D, but in high dimensions, yeah.
So I think what people can do or sometimes do is truncating it. Like it wouldn't be Gaussian, but a truncated Gaussian. So if this is kind of the distribution, they define a new distribution based on it by saying that if anything is above some range, then we ignore it. So the probability would be just like probability of this point would be the probability of a Gaussian having larger than that value. But then you need to do like later, if you do policy gradient type of method, then you need to be able to compute some say gradient of log of this policy, truncated policy, which may not be too difficult, especially if you use some kind of automatic differentiation.
I got it. Thank you.
All right. So okay. So this was about representation. Like in continuous action spaces, things are easier to represent, or can be easier to represent if we choose policy class in some nice way. But then, of course, this is only about action selection. What about optimization? Like, how can we optimize the performance of a policy when it is parameterized in some specific way? So is it easier or more difficult, or what? So I guess the point of this lecture is to talk about a few methods of optimizing policy's performance when policy is parameterized in an explicit way. And we see that we can do it. But then, of course, there would be some caveats. Maybe I should mention something else that, so these days, many papers use some form of policy for explicit policy representation. So you will see that they have something like policy gradient methods or hybrid methods between value-based and policy search methods, policy gradient. So they call it the actor-critical type of algorithms. This, I guess, practically they work well, especially when we have continuous action spaces. So if, for example, we have a robotics problem where usually we need to work with continuous action spaces because that's a command that we want to send to a robot. Then use of this type of direct policy search methods make things usually easier. Okay, so let's talk about performance measure. So what is the performance measure? This is basically what we want to maximize, and by searching in the policy space. So there are different ways that we can measure performance, but we focus on what we had before, which would be the expected return of following policy pi theta, which is essentially the value function of policy pi theta. So we want to maximize something related to value function. But also in this type of method, it's relatively easy to incorporate some other performance measure, for example, variance or some other risk measures, and do the computation. So, okay, the goal now is to find a policy that maximizes this performance measure. But then kind of the point here is that we are restricted to choosing policies within this policy space that is parameterized by capital pi of theta. Okay, so let's start from a simple case, and then we see what are the challenges, and then we gradually extend. So we assume that we consider the simple case that we only care about a single state, x. So we want to maximize the performance there. So the goal is to find a policy in pi of theta when the value of that policy at that state x is maximized, which also can be written kind of equivalently by saying that we want to find a parameter theta in the parameter space such that v of pi theta at that state x is maximized. So here, if I kind of visualize the state space as this box, we are essentially saying that this is our state x, and the agent always starts from that state x and kind of follows pi theta. And if it's random or the environment is random, we get different trajectories or rollouts, different trajectories. And then the goal is that in expectation, if we start from there, the return that we get is as high as possible. So this is kind of the idea. So here, if you recall, optimal policy is a policy that maximizes the value function at all states. Right? The optimal policy was always better than any other policy at all states. So, so if we choose pi star, the optimal policy, it not only maximizes the value function at this particular state x, but at any other x prime that's in that state space. So this is great. But the kind of the catch is that the optimal policy may not be in the space of policies that we represent. So this basically means that maybe the neural network that we use cannot represent the optimal policy because it doesn't have enough parameters or enough depth or anything. Or when maybe we chose a very simple policy class where the optimal policy does not belong there. So it is possible that, okay, so if maybe I can visualize now the space of policies that are induced by theta. So maybe what is happening is this optimal policy that is outside of this space. So there's this kind of like approximation gap or policy approximation error that prevents us to represent the optimal policy exactly. So what happens in that case? So if pi star does not belong to that policy space, like what I'm showing here, we may not find a policy that maximizes the value at all states. So in that case, what we want to do is that maybe focus on the only state that we care about. So I'm showing you the graph from previous slide. So maybe we only want to focus on making the value function of this specific point as high as possible, instead of having a value function that for all states is as large as possible. Is this clear? Okay. So I guess the consequence of this is that depending on where we choose for the initial states, the policy that we may find that optimize this performance measure would be different. So if instead of that point, I start at that point, the green point at the top, then the policy that we find, the best policy that we find in that policy space here might be different. So the result is that the policy, the obtained policy, is going to be initial state dependent. And if we change it, the policy, the optimal policy within, so this is optimal policy within, not the globally optimal policy, within pi of theta might change. Okay, so maybe I can, this is best, or so we can be careful about this, not to confuse with the real optimal policy. Okay, so this is just basically give you an idea that if we choose a policy class and the measure is maximizing the performance, the value function at one point, depending on what that point is, the performance, the policy that we get would be different. Now, that was extreme, so it was only one single point. We can talk about a case that instead of one single point, we choose from a set of points. So instead of just one point on the policy space, instead of one single point, I say that, okay, maybe my initial agent starts from this region in the state space, and I want the performance to be maximized for the average performance in that set. So the way that we can talk about this is that suppose we have an initial state that the agent starts, is distributed according to some probability distribution rho. And then the performance measure, we define it as the average of following pi theta when its initial state is according to rho. So this is basically with saying that we take the value function of that state, x, follow pi theta, and then we take average according to distribution rho, which is, of course, the same as writing that this is the expectation of v of pi theta of x when x is distributed according to rho. And we denote this by j of rho of pi theta. Or if we want to make it kind of simpler, I may sometimes write j of pi theta. Or in some other cases, I want to avoid extra notation, I may just write j of theta or j of rho of theta. So this is kind of, we identify theta and pi theta. So this would be the performance measure that we are going to talk about for the rest of this lecture. Any question? Okay, so as before, as we had for the single state case, we know that the optimal policy pi star maximizes just this j of rho. And we have, so as a result, I mean, is that j of rho of pi star is greater or equal to j of rho of any policy in that policy class. But if pi star does not belong to that, if pi star does not belong to, okay, I've written it all right. So if pi star does not belong to that policy space, then the inequality can be strict, or is going to be strict. So it would be always higher value. Okay, so we have this performance measure. In policy search methods, we want to find the maximizers of this performance within this policy space. So we maximize J of rho of pi theta, and we call it, say, pi bar instead of pi star. So these are maximizers within that policy space. So this notation, pi bar, is not a standard notation. So pi star is more or less standard, but here I just use pi bar. Okay, so what we have, as the case of single state, if I choose rho, we may get different optimizers, different pi rhos. So pi rho would be essentially a function of, pi bar would be a function of rho. So if I want to emphasize the dependence on the initial state, I would write initial state distribution, I should write pi bar of rho. And I guess as I mentioned in the previous slide, I may simply just use J of rho of theta instead of specifying that this is for pi. Okay, any question? So can you give me some idea about how easy or difficult it is? So everything's clear?
So is this performance measure the same as expected returns?
This is expected returns, but when the initial state is coming from distribution rho. So it's an average of expected return when, because let's see, this is, yeah, I guess that's a good point. Pi of theta, sorry, V of pi theta is the expected return, right? When we start from state X. So this would be expected return if initial state is X. Okay. And now I'm taking average of it with respect to rho.
Okay, thanks.
So is the reason we're formulating it this way because we can't necessarily represent the optimal policy in capital pi sub theta?
Well, I guess the reason, I guess you can say that way. So the reason that we have it as an integral of something like here, or expectation of something, is that we want to get a single performance measure, like a scalar, as a performance. So we need to convert performance to one single number, and that's the single number. But the consequence of this is that if we choose it, that the consequence of pi star not being in that policy space is that depending on how I choose rho, I make a different policies that maximize this performance measure. If pi star was a member of capital pi of theta, the policy space, then it wouldn't really matter what rho I choose, because optimal policy would be always optimal for whatever rho I choose. Does it clarify?
Yeah, I think that makes more sense because before we were thinking more about, I guess, just caring about the states in general, right?
Mm-hmm.
But here, but here we're limited by the policy itself.
That's right. So I guess that's right. Like there, we were thinking of finding a V. We were trying to find a V pi star such that it would be greater or equal to for all possible pi's, right? So, and for all possible states too. Okay. So it was like finding a V. So if this is V of pi, this is V of pi star, that is always larger than any other V pi. So the comparison point was that we are always, for any state X, we are always better than other policies. And those methods, like value-based methods, could guarantee that. But here we are going to, so this is not like a scalar performance measure, but it's a performance measure that is defined for all states. But here we want to kind of convert the performance of any of these policies to a single number and say that the one that has the highest number is the best. So we convert it to instead of set of equations, maybe you can say, we want to convert to a single number. And by taking average over rho as this way, we are converting it to that. But then if we convert to a single number, if the optimal policy does not belong to that policy space, then choice of rho would matter.
Right, that makes sense.
Okay, perfect. Okay, so so here the idea is that the question is that, okay, so how can we solve this optimization problem to find a policy that maximizes the performance J of rho? So we know how to represent the policy, or in principle, we know how to measure the performance. How can we optimize it? Well, it suggests that, well, we consider it as an optimization problem and then try to use many different optimization methods that people have developed in the past centuries, past few centuries, I guess, to solve this problem. But then this is an RL problem, so it has some differences with kind of a generic optimization problem. Some of them are, you can think of it as challenges, some of them are kind of opportunities. So the challenge is that, like one important challenge is that the value of J of rho is not easily available. So it is not like a function that we call and we get J of rho, but it comes from it is average value function of a policy. So the agent should interact with its environment and try to estimate the value function and then average it over all a set of state space or set of states in the state space in order to at least estimate this J of rho. So this is not easy computation. So this is one challenge in general. But kind of the opportunity is that there we have a lot of structure in the value function. In reinforcement learning problem, for example, value function satisfies the Bellman operator. So we are still talking about value, maximizing the value of a policy. So maybe we can benefit from these properties of value in order to design perhaps more elegant algorithms that are tailored to RL problem. Okay, so we want to use optimization methods. Broadly speaking, we can categorize them depending on the amount of information they need about the performance or objective measures that they maximize or minimize. So zero-order methods are those methods, like we can call zero-order methods and first-order methods and second-order too. So zero-order methods are methods that only use the value of the objective at various cohering points. So if I want to say maximize f of x for some x in some state space or input space, so these methods only use the value of, say, x1, x2 at different cohering points and try to maximize it. So in the case of our problem, these methods try to compute J of rho of theta at various thetas in order to guide the optimization process. And then we have first order methods, which in the case of, so this would be 0, the first order method would use the gradient information or derivative information. So they use f prime of x1 and f prime of x2 and so on. So they can also use the value, the zero order information too, like the value of the function itself. So in our case, we would compute gradient of the performance, or we want to compute gradient of performance in order to guide the optimization. And gradient descent or ascent type of methods and stochastic variance of them are kind of quintessential first order type methods. So I think usually in probably course in RL, people talk about first order methods and talk about policy gradient type of algorithms. But here I'm going to talk about first zero order method and then kind of get to the first order method to have a better kind of view of the problem. And that's why I call the lectures titles policy search methods instead of policy gradient methods. So today I'm going to talk about zero order methods. Okay, so maybe we can have a few minutes of break. Now it's 3 minutes past 1. Maybe we can have 5 minutes break, start at 8 minutes after. Okay, so let's continue with zero order methods. So here we just want to use the information about the value of this performance measure, J of rho. And we don't use any gradient information. So we start from the case of when the policy parameter space theta is finite. So we have only finite number of possible policies. And that this helps us understand some of the challenges. And then we extend it to the case that this policy parameter space is continuous. So the assumption is that we have a finite number of policy parameters, and as a result, finite number of policies. So this is the policy space, which is defined as before. Now the goal is to find a policy theta such that this performance measure is maximized. So this is kind of easy if we compute, and the idea here is that to compute just this performance measure for each of these policies, for each of these, say, m policies, 1 to m, and then choose the maximizing value. So this is going to be easy, at least in principle. The main issue is that how to compute J of rho of pi theta for all those m different policies. So here I mention kind of, at least in principle, maybe because, well, if m is like 10, 100, 1,000, something like that, it is easy. But if it is 10 to the power of 40, it is still finite, but we can't really do this search that way. But that's why I say principle. But the idea is kind of clear, hopefully. Okay, so now a question. How can we compute this J of rho of pi of theta for one of these policies? So give me some ideas.
Monte Carlo.
Okay, that's good. So how do you do the Monte Carlo estimation?
So we run a bunch of episodes and take the first step of each episode as one sample, something like that.
Right, yeah, okay, so I guess you need to modify. So I guess one question we have to answer is that first, how do you choose the initial states? And I guess the other is that how do you estimate the value for each of those states? And you can, I think your idea is that use the Monte Carlo to estimate the value by maybe, because Monte Carlo estimate provides an unbiased estimate of value. Is that maybe kind of close to what you're thinking of?
Yes, yes.
Okay, yeah, so that's kind of the general idea. So let's try to kind of develop it. Okay, so the performance measure is an expectation of value function at state x when x is distributed according to rho. So we can try one ways to do it. One way is that we can compute v of pi theta for all states. And how can we do it? In principle, we can use any of the policy evaluation methods because policy is given, you want to compute the value function for all states. And then after that, we take the average, the weighted average according to rho. So if state space is discrete, then we can write it essentially after computing using policy evaluation method to get to v of pi theta for all x's. I just take the weighted average of them and take summation of them. But the problem is that the computation of v of pi theta itself is not going to be easy if the state space is large. And also, if state space is large, so for example, it's a continuous domain, continuous state space, this summation becomes an integral, and the computation of integral might exact computation of the integral is going to be difficult. So even though we can use policy evaluation method to compute this v, at least approximately, but I'm going to talk about different methods, which is basically doing some kind of Monte Carlo estimation. So now the alternative is that computing an unbiased estimate of j of rho of pi theta using MC estimation. So we do it essentially in two steps, just to see kind of two sources of error in some sense, or inaccuracy. One is that we assume that v of pi theta is known, and now we want to estimate j of rho of pi theta. The other is that we assume that g of pi theta is not known, but we use returns. Instead of v of pi theta, we use returns g of pi theta in order to estimate them. And we know that this is kind of going to be a reasonable approach because returns an unbiased estimate of the value function. Okay, so first we start from the case. Maybe before that, any questions so far on the idea here? Okay, so we assume that we know v of pi theta, and we want to estimate j of rho. If samples are from rho, distribution rho, then we know that v of pi theta of x is going to be an unbiased estimate of j. So what essentially we have here, and we need to add x there. So when x is coming from distribution rho, expectation of value function when x is coming from distribution rho is exactly like the definition of expectation, v times rho, weighted by rho, which is the definition of the performance. So if I have a kind of random x coming from rho, that would be an unbiased estimate of the performance measure j of rho. And if we have n independent samples from the same distribution, then my estimator can be 1 over n of summation of v of pi theta of each of xi's. So essentially, if this is the state space, I choose xi's from the distribution of rho, and then take the average of it. And this would be, again, unbiased estimate of the performance. This performance also, this estimate also has some variance because we are sampling instead of computing the expectation exactly. And the variance behaves like this, that it would be variance of v of pi of theta over x, so randomness comes from choice of x, which is coming from distribution rho, divided by n, because we have n independent samples. So this is going to be the variance of our estimates. Okay, is this clear? Any question? Okay, so we have an estimator that is unbiased, and it is also has a variance that goes to 0 with a rate of order of 1 over n. So this is good, because it means that if we increase n, then our estimator would be more accurate. So variance is, of course, a measure of dispersion of the value function across states that are sampled according to rho. So let's think about some extreme cases. Maybe one is that the value function is a constant as a function of state x. So if we have pi theta x is constant, then the variance of it is going to be 0, right? So there wouldn't be any variance, and our estimate kind of 1 point would be enough to estimate that j of rho. If the value function is changing, but changing slowly, then the variance would be small. And if the value function is changing, so if the value function is like this, it's going to be small. And if the value function is going to change a lot, the variance would be high. Okay, so I guess the other comment that I have here is that the variance is a function of the policy pi theta. So for each policy, we get a different variance. But for all of them, the behavior as a function of n is the same. So it could be going down as n is increasing. Okay, so this is, that was the first step, assuming that v of pi is known. Now what happens if v of pi is not known? So here, second step, we replace v of pi with its return. Return is an unbiased estimate of v, value function. So that makes it kind of reasonable. And how can we compute the return? We had seen it before. So g of pi of x requires us to start the agent from state x and then follow pi theta. So we are doing a rollout from x. And then depending on whether the problem is episodic or not, like we go until the end of episode, or if it is continual task, we go until infinity. Of course, in practice, we don't go until infinity. We truncate after some point. But in the framework of continuing task, the end of episode is infinity. Okay, so if we do this, again, g of pi of x, when x is coming from distribution rho, is an unbiased estimate of the performance measure because of these identities. We have expectation, we take expectation of g of pi with respect to when x is coming from rho. We do conditioning over x. So we write it as expectation of over x and then expectation condition on x. So here x is considered fixed. So all the randomness in j pi theta comes from randomness after being at state x. So which includes the randomness of the next states and randomness of choosing the policy, the action according to policy. So this has a randomness, but that is this expectation by definition of the value function would be the value function itself at state x. So we get v of pi theta at state x. Now we take expectation with respect to rho, and it becomes j of rho of pi theta. Okay, any question on this? Okay, so again, so that was only for one sample x. If we have n different samples, x1 to xn, all from the same distribution, then we can form, we can take the average 1/n of g pi of xi, and then this would be our unbiased j hat of n would be an unbiased estimate of j rho for that policy pi theta. And then we can talk about, we can compute, we know that it's already unbiased estimates for j of rho. So that estimator j hat is an unbiased estimator, and it has a variance which can be calculated. I guess you can take a look at it at the lecture notes, which I'm going to post soonish. So it would be variance j hat of n would be 1/n. So we have this 1/n behavior. And then it has two terms, kind of. Well, two terms. One is the variance of a value function over randomness of being x. So this is exactly the same as what we had in this first case, that assume that v pi is known. So this is the variance of changing the x, or randomly sampling x from the distribution rho. And it only depends on v of pi. And the other is the variance. The other depends on the randomness of the return, because return has some stochasticity. So we compute conditional expectation of the variance of the, or conditional variance of g of pi theta. So this is the this is the variance of g of pi theta for one particular state x. And then we take expectation over all states to get the average variance contributed by that. Okay, so if we have a finite number of parameters in policy space theta, or parameter space capital theta, then we can essentially do this computation or calculation for each of them. And what we have is that the performance, j of rho of pi theta of I, is going to be j hat of n of that pi theta, plus some term that behaves order of 1/square root of n. Right, and here essentially I'm kind of hiding a lot of things in the order notation, including that this statement is true with, say, high probability, because these are kind of random variables, like j hat is a random variable. So with high probabilities within 1/square root of n of the true j. So that's, sometimes people use this notation of order of p. It says that we have probabilistic elements in the order notation that are kind of not shown. Okay, so we can use, now we have all these estimates instead of maximizing. So remember, the goal is to solve this problem. So that would be theta bar. But instead, we are computing argmax over theta of j hat of n of pi theta. So here maybe it's more accurate to call it pi hat, and then pi hat induces pi of, sorry, theta hat, and theta hat induces pi of theta hats. Okay, this one, first of all, is this clear what has happened? Okay, so I guess you have to be more interactive a little bit. We are only a handful of people now.
So is the first expectation over rho and the variance as well?
Yes, so this, you mean this one?
Yeah.
So that would be, yeah, so that would be x coming from rho. But the variance is coming from randomness variance is conditioned on x. So the randomness of it is not coming from rho because x is already selected according to rho. So there's nothing stochastic or random about x, but it is the randomness coming from following policy pi theta and getting the return. So this is like if I first randomly choose state space, I choose x randomly, and then from that point, I get different returns because of different trajectories. And this variance is the variance of the returns that we get through these trajectories. Does it make sense?
Right, it makes sense. So the first term is like from the environment and the policy, and the second term is caused by rho.
Second is caused by rho, so maybe I can write.
Gotcha.
So this is the variance here coming from x coming from rho here. So like the outer operator, like either expectation here or variance here, both of them, the randomness coming from x coming from rho. This first term has an internal component of operator, maybe you can think of it, which is the variance, which is not function of rho.
Makes sense.
Perfect. So a question, if we do this process, like compute theta hat or pi of pi hat, in this way, by computing the maximizer of j hat of n, what might happen? Like, is this a reasonable procedure? Maybe first of all, do we find this pi hat that we find here? Is it going to be the same as pi theta bar here? Pi theta bar here?
I guess as n goes to infinity, then you'll be guaranteed that j hat of n will be different enough, or sorry, the difference between the different j hat of n's with respect to theta will be large enough that the noise will be smaller than the difference between them, I guess is what I'm saying.
Right, yeah.
So then you'll get the right answer. But
that's right. What happens if n is not infinity?
Well, then the noise might be larger than the difference between the states, so you might choose the completely wrong one, I guess.
Right. So yeah, exactly as you mentioned. So if n goes to infinity, then j hat converges to j, because j hat essentially, so what we have from here is that the difference between j and j hat is order of 1 over square root of n. So n goes to infinity, the difference goes to 0. And then, so doesn't matter which one we maximize. But if we have a small n, then it is possible that we choose a maximizer that is kind of the wrong maximizer. So we choose a theta hat here that is different from theta bar. But then we can argue that the difference between these thetas, or the performance of these thetas, are not going to be very large. They're going to be in the order of 1 over square root of n, because we made a mistake. Yeah, let's see if I can visualize it. So I'm kind of showing. Okay, so I have a finite number of policies. Say pi 1, pi theta 1, theta 2. I just compare two of them. And then say I use green for j bar. So the value of, so that would be j rho of pi theta 1, or maybe okay, it's going to be a crowded figure, so maybe just theta 1. And this is going to be j of rho of theta 2. Okay, So I guess this is better. Okay, but we are having something that is an estimate. So we are finding something that is square root of n larger or smaller of that. So we are going to have, maybe I use orange. We are going to be in this region for our estimate of j hat of n of that parameter. And the same for here. And this region is order of 1 over square root of n. So suppose what happens is that you're kind of unlucky. For theta 1, we select these points. The value, estimated value, would be kind of smaller bound of that confidence interval. And for here, we have the top of it. So what might happen is that we choose theta 2 instead of theta 1, which is going to be a suboptimal choice. So I think this part is clear. But then if we make such a mistake, if it is possible to make such a mistake, this basically means that the difference between these two values, between the actual value of theta 1, j of theta 1 and j of theta 2, is going to be not larger than 1 over square root of n, like order of that. So because they're already close enough that we make a mistake. So even if we make such a mistake, the difference between these two is kind of like the suboptimality gap that we can think of, is going to be smaller or in the order of 1 over square root of n. So this is a good news because it shows that if we are increasing n, it is possible, if we have finite n, it is possible that we make a mistake, as in this figure, but the mistake that we make is not going to be very large. It would be order of 1 over square root of n. Is this clear, the argument? I mean, I try to visualize it instead of write it mathematically, algebraically.
Yeah, it makes sense to me.
Okay, perfect. So yeah, I guess these are basically what I just saying. As increase n, the error in estimating decreases and the probability of selecting optimal policy increases. But then this increased accuracy comes at the cost of increased computation or increased number of samples required. So the number of computation and samples would be order of n times number of parameters, which was finite in this case, number of rollouts. And depends on how long the rollouts are. Like if they're going to be very long episodes, then that would be a large sample complexity. But if they're small, that wouldn't be too bad. But basically, by increasing n, we get more, we need more computation. Okay, so what I kind of argued in visually can be formalized, basically saying that under some assumptions, like consider that the policy that we find by optimizing j hat of n, and assuming that all returns are Qmax bounded, so this is assumption to make things easier. We can relax it. So if they're Qmax bounded, say everything is between some number, minus 10 to plus 10, for all policies and for all x's. Also, we suppose that the number of policies or parameters describing policies is finite. Then we can provide this guarantee that for any delta larger than 0, so this is going to be probability of error, this statement is going to be true with probability at least 1 minus delta. So just to have something in mind, like maybe choose delta equal to 0.01, so 1%. So this then we say that with 99 probability of 0.99 or 90%, 99% chance, this is going to be true. So this is a probabilistic statement. So what is this saying? It's saying that the performance, the true performance of theta that we find using optimizing j hat of n is going to be larger than something which is, well, the optimal performance, the maximum over thetas of j of rho of theta. So this is the performance of the best policy in that class optimized according to the true performance j minus some gap, which is minus 2 times q max of 2 square root of 2 times logarithm of 2 times size of parameter space divided by n. So visually, this means that, okay, so if this is the performance, essentially this is like what I have here. This is the optimal, for example, but I select this one. The real performance of this theta 2 is going to be close to optimal minus some gap, and this gap is order of 1 over square root of n, and that order is going to be this specific value, 2 times q max, 1 over square root of n, times logarithm of some terms that is divided by, it's like 1 over delta. So if delta is smaller, that would be larger, which basically means that if we want to be more confident about it, we need to kind of have a potential of having a larger gap to be confident, with higher confidence. And also it depends on the size of the parameter space. So it's a finite, so, but in a logarithmic way. So if we have say 1,000 parameters, that would be logarithm of 1,000. So it's not going to be very large. If it is 10 millions, that's still okay. But if it's infinity, so if it's continuous state space, then these arguments should be modified. So this result does not hold, or the result shows a kind of useless bound because this term diverges, goes to infinity. Okay, is everything clear so far?
I had a question about the 1 over n in, I think it's on the previous slide.
Was it?
Yeah, or sorry, 1 over the square root of n. It was, okay, maybe not this far back.
Here or?
Like the big O. Yeah, so the,
okay, here,
like the plus or minus error.
Yeah.
So is the 1 over square root of n, does that come from the fact that the variance is equal to 1 over n times some value? So the standard deviation would be some value over 1 over the square root of n?
Yes, that's right.
Okay.
So,
yeah. And yeah.
Squared value of the error, so.
Yeah. And okay, so the other question I had was, on the slide that you covered most recently with the Q max.
Mm-hmm.
So does this require us to know what the Q function is?
Not really, because you can provide some, well, this is a kind of general theoretical result. It says that if things are like this, if everything is bounded by some number, then this is the guarantee you can get. But if you actually want to calculate that value, usually in many problems, you know Q max. Why? Because you usually design the reward yourself, so you know the maximum reward that you can get. So for example, you know the rewards are between -1 to +1, right? So if the rewards are, if you know the rewards are between, say, -1 to +1. So that would be your R max. So this is going to be maximum reward. But then we can get that if the maximum reward is something, then Q max is going to be R max divided by y minus gamma. And you can see this from the definition of the value function, because value function, not writing everything completely, but it would be gamma k r k, for example. So if each of these terms is bounded by R max, so this would be bounded by R max divided by sum of k, which would be...
Oh, okay, it's like an infinite sum, right?
Yeah, so it would be 1 over gamma. So if gamma is, say, 0.99 and R max is 1, then Q max would become 100, right?
Yeah, yeah.
So then you have 100 here.
Okay, okay, cool. So yeah, I was just like looking at this equation, and you can kind of, if you move the Q max term over to the other side and move the J theta hat over the other side, you kind of get like the difference between the max and J hat theta is bounded by that.
Yeah, exactly. So the difference between the performance, like if I compute first term minus second term, it would be upper bounded by 2Q max of whatever term I have here.
Okay, okay. And then, yeah, as n goes to infinity, then that term basically becomes 0, so then they converge.
Yes, that's right.
Awesome, cool, thanks.
Okay, so okay, so that was for finite case. So I guess maybe the point was we have variance coming from different sources. One is that randomness of X inputs coming from rho. The other is the variance of return coming, which we use instead of the value function. And we can provide some guarantees. So this is a sensible approach. But what if the parameter space is not finite? So what if it is continuous? How can, in that case, we cannot evaluate J hat of n for all parameters or all policies. It's infinite number of them. So there are different ways to kind of search in that space, continuous space. And so there are many methods, but one basic method is doing random search. The other is simulated annealing. And the other is that many different evolutionary algorithms. And kind of another way is to also try to approximate gradients using first order information. So it's numerically approximate gradient instead of a more analytical way. I'm going to talk about it maybe a bit later. But let's talk about these methods just to give you an idea of what we can do. So random search is easy. We have a parameter space. So I'm showing another figure. This is the parameter space, not state space. I randomly pick different points, theta i's, and then for each of them I evaluate J hat n of that particular theta for each of them, and then pick the one with the highest value. Okay, so that's, now suppose that the best parameter in that space, which is continuous, is, say, this one. So this is what we had as, okay, theta, maybe I shouldn't have used reds. Yeah, okay, so that's okay. I usually use red for something that needs to be corrected. So that's a point, one of these points, but we don't have that point as our sample. But the idea why this random search works is that if I add a lot of points, choose randomly a lot of points, some of them becomes close to like if I zoom here, at this point becomes kind of close to the optimal one. So gradually I fill the space of all parameters, and gradually the closest point to that optimal theta bar becomes very close to that. So when I compute the performance of that, so at this point, the performance of it is going to be kind of close to the performance of theta bar. And that's why if I keep choosing many m's, I would get a better, gradually better performance or better policy. So the idea here is that, okay, so with large enough m, one of theta i's might hit close to the optimal that we have there. And here, okay, so here I'm using it theta hat instead of theta bar because this is based on j hat and not j rho. And also, I guess the other thing is that if n number of rollouts is large enough, the difference between j hat and j rho would become smaller and smaller. It would be like 1 over the square root of n. So kind of with similar argument to what we had before, things should be still working fine. So the algorithm would look like this. I mean, this is what it's basically described. So we have a distribution row which says how we should choose sample parameters in the parameter space. We have a number of rollouts, and we have, say, maximum number of iterations, which can, of course, go to infinity. So we choose a parameter theta 1 equal to theta bar, theta prime of 1 from that distribution, and then evaluate it. And then at the next, from iteration 2 onwards, we draw a new parameter theta bar of k from that distribution, evaluate it, and if that parameter has a better value, so if j hat of n of this pi prime is better than performance of theta k, pi of theta k, then I replace it. Otherwise, I just keep the previous value as of theta k and keep doing this. So randomly choosing point, if it's better than before, that would be our new point. Otherwise, we discard it. So this is the random search. So I'm not going to prove this, but we can show that, like there is in lecture notes, but we can show that random search finds the optimal points, but asymptotically. So eventually we get arbitrarily close to the optimal policy. So that's a more accurate statement. But then random search is not the most efficient way to search a parameter space. And kind of the reason is that it is not benefiting from the value of previous evaluations, so value of previous parameters that have been evaluated in order to guide its search. So it always chooses samples from the same distribution nu. So this distribution nu, it always samples from the same distribution. And as a result, it's kind of like ignoring whatever happened in the past. But that knowledge can be helpful in order to guide us to go to the kind of focus on promising regions of the search space instead of blindly sampling from the same distribution over and over. And the way that we can dismodify it, or the idea here is that maybe we should try to adaptively modify the distribution nu to make it nu k as a function of iteration as a function of previous evaluation. So if we adaptively change that distribution based on what we had before, maybe we can have a better algorithm. So I think, yeah, random search may not, I mean, it works probably in small problems with small parameter space reasonably well, but like if you have few parameters, 5, 10, I think it should work okay. But if you have millions or thousands, it may not work very well. I guess the other, but I believe there have been some work that just tried this and showed that the result wasn't too bad. But I can't remember the exact reference now. Okay, so next let's talk about evolutionary algorithms. So this is not something that people usually talk about in a reinforcement learning class, but as I argue later, it is good to know. So I thought that it's a good idea to talk about, since especially it is similar, at least at some level, to random search and the idea of adaptively changing that distribution. Okay, so large class of optimization methods are inspired by the process of evolution. So evolution would be kind of heritable characteristic of individuals in a population change over generations due to a process of natural selection and other processes like drift, genetic drift. So the outcome of evolution is that it leads to adaptation of individuals, which adaptation means that they become better in some sense to live in their habitats. So they adapt to their habitat. If they require to, I don't know, walk faster, they gradually evolve to walk faster because that's important in their habitat. For example, if there's a lion in that environment, it's good to be able to run fast. So there are many, okay, so evolution, well, it's in nature, but we can get inspired from evolution in order to design optimization methods. And I mean, since decades ago, people have thought about evolution, designing optimization methods based on this evolutionary process or evolution principles. So the general way that we work is that we say that a solution to an optimization problem, the parameter that optimizes things, so for example, theta, we consider as an individual in a population. So we have a population of individuals, which means that we have a population of thetas. And then the value of function that we want to maximize, like we want to maximize j of, say, pi, that value would become the fitness of that individual. So how fit that individual is to live in its habitat. And then the fitness determines whether they have a chance to go to the next generation or not. Like fitter individuals have higher chance to go to the next generation compared to the less fit ones. And here, in order to make it an optimization problem or use it to solve an optimization problem, we define fitness as the value of that function. And then we try to emulate the process of evolution at some level. So there are like natural evolution has many components like mutation, genetic mutation. We try to imitate something like that. We have reproduction or crossover, which is like two individuals, two parents reproduce and make a kind of a child, an offspring. So that's a crossover reproduction. And the other process is selection, is that not all new offsprings would have a chance to go to the next generation. Some of them would perish. So, and only a few of them have a chance to go to the next generation and then repeat this process. So there are many ways to interpret or implement each of these, like crossovers, mutations, selection. So it's a huge literature. It has been active research. So I'm trying to remember when was the last, I guess, evolutionary methods, but it's probably almost as early as AI, like maybe in 60s probably. I guess John Holland was one of the first people who worked on it. And it has been, I guess, very active in 90s, 80s, 90s. But the community, I guess, in general is different from the RL community or computer science community even. Like many times it happens in some engineering fields because in practice these methods would work more or less. If you have a lot of computation, they work, they usually find a good solution. I mean, this is maybe a kind of, at least my impression from computer scientists, at least in North America. Usually, I guess in computer science departments, research on evolutionary algorithm hasn't a big topic. So I think computer scientists usually at least used to not like evolutionary methods very much and consider that that research is not of very high quality. And to some extent it is right, because many of the papers that have published in 19th and 2000s, they basically was choose this one evolutionary algorithm, modify it through some heuristics, and then try it on their problem and get a result. And yes, great, you get a good solution, but there wasn't much theoretical work like showing that why this is optimizing something. It was just practical or empirical studies. So that was the thing. But there are, of course, some sort of research on theoretical properties of it. And it has been done in RL too, like using evolution methods to solve reinforcement learning problems. Maybe one can say that there has been more recent work on that. So I would say, I don't know, I haven't checked very exactly, but 10 years ago, 15 years ago, I guess it would be very difficult to publish a paper that was an evolutionary methods at a top machine learning conference like ICML or NeurIPS. I don't know if there existed or not, but if there were, it was rare. But then I guess nowadays we see occasional papers there. So I guess community becomes changing their mindset. But also I guess we can say the same thing about neural networks. I think in 2000s it was difficult to publish a neural network paper at NeurIPS compared to, say, kernel-based methods. But now it's difficult to do it otherwise. Okay, so it's kind of just history a little bit. So there are many variations to do it, like genetic algorithms, genetic programming, evolutionary strategy. So I'm talking about the simplest method. It's called evolutionary strategy 1+1. So that's the name of it. And this works somehow like this. Or, yeah, I mean, this is the algorithm. So we get an initial point in the parameter space. I modify it for our RL problem. We have a number of rollouts, so that's RL part and number of iterations. Then we have this initial standard deviation of so-called mutation operator. So that's the standard deviation, sigma 1. And then we have these adaptation parameters, C plus and C minus. C plus is positive, C inverse is negative. So this is for the evolutionary strategy, parameters of evolutionary strategy. So first we compute the performance of the first policy. And then for each iteration, so what we do is that first we generate a random number or random vector, not a number, from a Gaussian distribution that is isotropic, so with covariance matrix being diagonal, and then generate theta prime of k as theta k plus this noise that is multiplied by sigma k, that's standard deviation. So initial standard deviation, we multiply it. So that basically says that how much noise we add. And now we evaluate it. And then we do something similar to what the procedure for random search. So if the performance is better, the performance of this new pi of theta prime is better than the previous performance, then we substitute pi k plus 1 as pi prime of k, what we generated. If not, we keep the previous value. But also we have this process that we change the variance according to this adaptation rule or standard deviation. So if it was positive, we increase the variance. And if it is negative, like we get a worse point, we decrease the variance. So I guess we can think of the idea is that if it was successful, the perturbation gradually becomes larger. But if we are not successful, it tries to become smaller and smaller. So maybe if you're optimizing some points, if yeah, I guess maybe we can think of it if we are at this point theta k, and if we jump to a point that is better, now the variance at the next step, so this is a better point, we want to maximize, the variance would be larger. But if we jump to a point that is worse, maybe, sorry. So if we jump to a point that is worse, it tries to have a smaller jump, maybe just to come back or not. So this is a heuristic. So why it works is not necessarily trivial, but that's the kind of idea. So why this is an evolutionary process, of what part of it is an evolutionary? This is, first we talk about individuals. What are the individuals here? Each of these, I use different color. Each of these theta k's is an individual. So at each so at each k is an index of a generation. So we are at generation 1, 2, 3, 4, so on and so forth. The individual that we have is theta k. So there's only one individual at any time, kind of. Except that at this point, we generate an offspring from that individual. So there would be one offspring from that individual. So this process of adding some noise is kind of can be interpreted as having a mutation. If we interpret theta, the vector, as a kind of genetic material in code of an individual, this adding noise can be seen as a perturbing the genetic material, which is what mutation does. Of course, in nature, mutation is not a Gaussian distribution being added to a real valued vector, but that's the kind of idea. And then we have this process of selection here, which basically we check which one is better, the parent, theta k, or its child, theta prime k. If some of them is better, then that would be the next generation. So here, it is possible the next generation would be the same as the parent, so it doesn't change, or it's better that the child would become the next generation. So this is kind of like the evolutionary metaphor here. So any questions so far? I'm sorry that I have to go a few minutes more than 2 hours, but let's finish this part.
So in the case where the child is worse, you actually revert to the grandparent, I guess, like the k-1 instead of the kth?
Right, so that's a good point. No, that's a typo. I just keep one generation at a time. So I just revert back to the parent. Yes, so that's a typo.
Oh, gotcha.
Is the process clear, more or less?
So would it be better to mutate many offsprings and then take their max?
Yes, that would be probably better. And that's actually one of the variants. So, and I'm going to briefly mention it next, but that would be called the variant 1 plus lambda, and lambda would be number of offsprings. So that's how we encode it, or it's common to be encoded. So yeah, I think I have these things. So, okay, so yeah, I'm going to mention it just here. So this is evolution strategy. So this is called evolution strategy 1 plus 1. 1 refers to that number of parents. The other one is the number of children. So it's 1 offspring, 1 child, 1 parent. And so if you had more children, it would be larger numbers. So it would be 1 plus lambda. And if we have more parents, like mu parents, and lambda children, so that would be another procedure. The reason I mentioned this, like simplest method, is Is not necessarily because that's the best method, but because it's very simple to random search. It's random search will also we generate only one next byte, one theta prime, and then we compare it. But there wasn't any. But the difference was that the new, if you recall from random search, theta prime that we chose was coming from distribution nu, so it was sampled from some distribution. Here we are doing something a bit different. We are sampling from some distribution, but that sample is around the previous successful parameter, essentially. So we perturb a good parameter instead of just randomly point sampling from everywhere. So that's why this evolutionary strategy method might be better. So this has a guided choice of randomness as opposed to random search, as I explained. And the other reason that this I mentioned is that it has some theoretical analysis. So this is one of the methods that actually comes with some proofs of convergence for some class of functions. But more complex methods usually don't have any theoretical studies. I think, okay, so another modification that you mentioned is that it's called, so it's 1 and lambda and 1 plus lambda. So this case would be that we have a parent, K, that generates lambda offsprings, similar to before. Each of them have different noise, of course. And then here the competition would be only between the offsprings and not with the parents. And only one of the lambda offsprings get to the next generation. So this is kind of a notation that is common in evolution strategy, that if they write, maybe I should write in general, mu and lambda means that mu parents generating lambda offsprings, and competition is only between offsprings. If they have lambda plus, mu plus lambda, it means that we generate, from mu parents, we generate lambda offsprings, but the competition or selection would be among both of them, like both parents and lambdas. So here, in the case of only competition between lambdas, it is actually possible that the best you can find is worse than your parents. So actually the generation might become worse than before. But here in this second choice, second method of selection, you're always better than the previous parents because the best in the parent generation is already in the competition. Of course, this is under the condition that the this selection procedure is kind of deterministic the way I have here. Sometimes the selection has randomness in it too. And then that property that I mentioned might disappear. Okay, so any question?
So is there any benefit to excluding the parent for the next generation?
I'm not sure 100%. I think I would guess the idea, or at least the reasoning, would be that by excluding the parent, you kind of avoid getting stuck in local optima, because you are, for sure, you are exploring other points, or you have to explore other points. But I'm not sure, I don't know if there is any kind of theoretical guarantee for that. So. Okay, so evolution strategy, the way I explained it, and I guess usually, does not have any sexual reproduction. So there is no combination of parents to generate a new individual. So in some sense, this is like a sexual evolution. So there's no sexual part in it. But there are other evolutionary algorithms that have this reproduction component. The famous one is genetic algorithms. Okay, so some comments. is that evolutionary algorithms can be quite complicated algorithms. Like there is a lot of things that going on. There's mutations, different types of mutation. There is this reproduction, sexual reproduction. How to do it is not obvious, and there are probably thousands of different ways to do it. And the selection is, there are many different selections. It can be different choice of randomness. So basically, there are many heuristics that are inspired by nature. And the kind of the word is, it's inspired. It's not necessarily how the nature works, but it is how a researcher thinks nature works and then implement it as a kind of algorithm. And the performance is often evaluated only empirically, and analyzing them theoretically, it's not because people don't want to analyze them, but it's usually very difficult. I guess more recently, people have become more interested in understanding them theoretically, but still it is a difficult problem. Like, I am not an expert in the field, so I don't know what is the state of the art, but as far as I know, like we know results for ES 1+1 and some others, but not many others. Like most algorithms don't have any theoretical analysis. Okay, so one other kind of comment is that studying evolutionary algorithm or using evolutionary algorithm to solve reinforcement learning problems is a very kind of a niche area in the RL community. There have been some researchers who used evolutionary methods to solve these problems within RL community, but there are only few. And there are, of course, more in evolutionary computation field who use evolutionary algorithms solving RL problems. And then there are these all sorts of kind of papers saying that, at least we had in the past, that evolution methods are better than RL methods for solving RL problems, and then vice versa. So this we have, I guess we have these fights occasionally. So sometimes, or maybe often, they are not considered as a part of their RL research, but I think knowing about them is useful because of many reasons. I guess it's both of them are trying or can be used to solve the same problem, or optimizing the performance of a policy. But also, I guess beyond that, both evolution learning have been crucial adaptation mechanism for kind of getting to the point that we have intelligent species. Of course, not all species are intelligent, but we have relatively smart species like humans or apes or many other animals. And the way they can be smart is, part of it is because of their evolution, like they have evolved to have a kind of large brain with proper components. But also they have this ability, they evolved to have the ability to learn so that they can adapt during their lifetime. So if our goal is to design a kind of AI agents that have capabilities that are comparable to animals or humans, we may need to borrow ideas from both evolution and learning, maybe use learning for kind of adaptation within the lifespan of the agent and evolution across generations of agents. So yeah, so this is kind of maybe not usually considered in an RL course. It's not a part of RL course, but I think knowing about it is good. So I think half an hour talking about it wasn't a bad time.